So today we're looking at section 6C, which is entitled the normal distribution. And basically the normal distribution is just another way to, or even more specific case I should say, about talking about the spread of your data. In probably up to this point you probably may not have seen it referred to as the normal distribution, but you probably though would have heard it referred to as the bell-shaped curve. And if you look below here, just at this picture, that is an example of the bell-shaped curve. Essentially, what we're saying then is, whenever if an instructor ever told you, I grade on a curve, you're grading on a curve like that, then they're saying that 68% of the people then in the class were scoring a C. Another 14% were scoring a B or a D, and then an even smaller percentage scoring an F or an A. Over here in the text box, I say a little bit more about that, but truthfully, it's very rare for grades in a class to follow a normal distribution. I can speak from experience that most often you find them more of a skewed, in a more skewed pattern, that generally more folks are in that passing range and fewer over in the DF range. With that said, though, there are common occurrences, though, for where the normal distribution, the bell-shaped curve, does lend its, you see it quite often. And one common example is the height of adult men. And what I did is I showed you this through a progression of a small sample size and increasing up until I get to the total population of men. And you can see here with a population of 100 men, you're almost bell-shaped at that point. Increase the sample size and you can see we are right on track for a bell-shaped curve. Increase it even more and you are perfectly normally distributed. And then you look at the entire population and you would find that the height of adult men would be normally distributed, with that mean falling right in the center. Should be noted the normal curve, then the mean and the median are the exact same value, and then you have 50% of the people are higher than that average height and taller than average height, and 50% are shorter than that average height. Some other examples, I'll let you read those at your leisure, are other examples that would be following this normal shaped curve. Okay, flip it on over to our next page. Today is where I'm going to talk a little bit more about, why do we strictly look at 3 standard deviations above and below. I'll start here with this and still going on with, still going on with the 3 above and below, but on the next page we'll say explicitly why is it just 3 above and below. Here's what you'll be looking at. In general, you'll always have the mean sitting there in the center, and I'm just using that symbol mu. And then you can have 3 standard deviations above. So like you saw in the previous set of notes, then 1 standard deviation above would be the mean plus 1 standard deviation. So I'm just doing sigma for standard deviation. 2 standard deviations, the mean plus 2 standard deviations. And then that third, mean plus 3 standard deviations. You can go below the mean, and that would be the mean minus 1 standard deviation, 2 standard deviations, so that'd be mean minus 2, or mean minus 3 standard deviations. So that's what you're going to be looking at. I'm using the mean and the sigma here because I'm looking at the entire population instead of just a sample. Let's give you an even more specific example, very similar to what I showed you in the previous set of notes, but we're gradually working our way up to this idea of the normal distribution. You see a little bit more where we're going with this. So it says here that the average commute time from St. Petersburg to Sarasota is an average time of 52 minutes in the car. Standard deviation is 3 minutes. So that means then 1 standard deviation above, I'm going to add 3 minutes, so that'd be a 55-minute commute. 2 standard deviations, add 3 more minutes, so 58 minute, add 3 more minutes, a 61-minute commute. Let's go below and subtracting 3, so that's going to be put me at a 49-minute, 46, or 43-minute commute, and I'm just going to label this down here as commute time. And put this in minutes. Okay. Where we're headed is I'm going to ask you things like, what percentage of those that travel from St. Petersburg to Sarasota have a commute time between 49 and 55 minutes. And we're going to we're going to figure out what these percentages are that go in each of these blanks. But it should be noted that 100% of the commute times would fall under this curve. There would be, the rare instances that would take someone less than 43 minutes. There'd be the rare instance, maybe there's an accident or something, and it would take someone longer than 61 minutes. But the majority of the people are going to fall between 43 and a 61-minute commute, okay? So let's flip it on over. And that's the empirical rule. The 68, 95, 99.7, like I said, just call it the empirical rule. What that says is that it says that approximately 68% of your observations fall within 1 standard deviation above and below the mean. I'm going to go ahead and fill this in. 95% of your data is within 2 standard deviations above and below the mean. And then lastly, 99.7% is within 3 standard deviations above and below the mean. So that's the reason why I'm not going past 3, because I've almost virtually got 100% of my data when I look at 3 above and 3 below the mean. Okay, so that's explicitly why we had always been stopping at 3 above and 3 below. Now let's take a moment and let's figure out the percentages that go in each of those rectangles. So I'm going to take a moment and draw out a normal curve. As I said before, put the mean right here in the center. 1, 2, and 3 standard deviations above and below. And I'm just going to label that as 1 standard deviation, 2 standard deviations, and the 3 standard deviations. And then I'm going to go back up to what my notes were saying. It said that 68% of my data fell between 1%, fell between 1 standard deviation below and above the mean. So if that 68% is between 1 standard deviation above and below, that's going to put 34% in each of those rectangles. There, okay? Then your next piece of data said that 95% fell within 2 standard deviations above and below. So I want to figure out, okay, well, what goes then in these 2 rectangles? So to figure that out, so in the previous one I just did 68 divided by 2, and that gave me 34% in each. Well, at this point, I already have 68% because you can see that there's some overlapping here. So what I want to do then is I want to say 95 minus 68, which gives me 27% left to work with. So I have that 27% that needs to be divided between these 2 rectangles. So then I take that 27 and divide it by 2, and that should give you 13.5%. So I put 13.5% in each of those rectangles. Then your next rule said that there was 99.7% of your data was between 3 above and 3 below. So to figure out, okay, well then how much is left over for these next 2 rectangles, I do 99.7 minus 95. That gives me 4.7. Take that and divide it by 2, and that gives me 2.35%. So that's the percentage then that I want to go in those next 2 rectangles, 2.35. And then lastly, like I said a minute ago, 100% of your data is underneath this curve. So there's a minuscule amount then that is beyond 3 standard deviations in either direction. So to figure out that, I just do 100 minus the 99.7. That gives me 0.3 divided by 2. That's going to give you 0.15%. Very tiny percentage. So this one right here would be it's a different color. Get that. 0.15%. And this one also 0.15%. these percentages that I've just shown you here, I derived them for you, but they don't change. So, you can see on your formula sheet that we tell you, that you have a 68, 95, 99.7 rule. So you saw how, like I said, how I just derived it, but if you want to, you could just memorize all of these percentages. And hopefully you'll start to see the symmetry in it. As you do more of them, it wouldn't even be too big of a memorization on your part. Let's look at example 2 together, and then we'll be wrapping this up. Here it says the height of young American women ages 18 to 24 is normally distributed with a mean of 64 inches and a standard deviation of 2.5 inches. We want to draw and label our normal curve. So, average height, 64 inches. And then, actually, I won't even, I'll keep the inches in, that's fine. And then I will add 2.5 on the right, so that's going to put me at a height of 66.5, 69, and then 71.5. Going below, I would have 61.5, 59, and 56.5. I'm going to fill in my percentages like we saw from above, that this was 34%. Everything in here is percentages, so I'm not going to keep writing these percent signs. 34% in the middle, 13.5, working your way out, 2.35, and then lastly 0.15. And I will label this down here. You want to be sure that you always do that. This is height measured in inches. Okay, so now you want to be able to answer questions related to your sketch. So it says, what percentage of the women is between 59 and 69 inches tall? So you come up and look at, okay, here's 59 inches, and there's 69. And essentially what I want to do then is I just want to take and I want to add all of those percentages. You want to think about that there's a blinder here at 59 and there's a blinder here at 69, and you only want to tabulate what's between those two, nothing beyond. So if you were to add those percentages up there, you would find that that's 95%. Another way to look at it is that 59 is 2 standard deviations below, 69 is 2 standard deviations above. That's part of your rule. 95% of your data is between 2 above and 2 below. What percent are shorter than 61.5? So here's your 61.5. Now you want to be shorter than that, so you go to the left, and anything over here to the left gets included in, even someone shorter than 56.5 inches. 56.5. So 13.5 plus 2.35 plus 0.15, that puts you at 16%. So 16% of the population then is shorter than 61.5 inches. What is the probability? We'll talk about the difference there. Probability just means your answer is going to be expressed as a decimal and not a percentage. Picked at random is taller than 69 inches. So taller than 69 inches, here's your 69. You want to be taller than that, so that's going to be going to the right. That would mean to add these two pieces together, that would give you 2.5. Remember, that's measured in percentages, so since you want probability, you just change it to a decimal. You move your decimal 2 places to the left, so 0.025. That would be your final answer there, probability. Probability that a person's between 56.5 and 71.5, so between here and here. So it's not quite your entire normal curve, it's excluding the little tails out there. So that would be 99.7. Since you want it, though, again, as a probability, we change it to a decimal, so 0.997. That would be my probability. Part E, what percent is shorter than 64 inches? So there's your 64. 64 inches, that's your halfway point. And so it should make sense to you then that 50% then is below that. But you could just go through and add these numbers together, and you're still going to find that that's 50%. How tall are the middle 68%? Start in the middle, and you want to keep going on either side evenly until you reach your number here. Your target number in this case is 68%. So I'm going to go 1 unit to the right, 1 unit to the left. Automatically then I'm at 68%. So then I would say that would be between 61.5 and 66.5 inches. How tall are the tallest 0.15% of women? 0.15%, and you want to be the tallest, so that's going to put you over here on the right, they would be 71.5 inches and taller. Okay, so hopefully that gives you a good idea of what we'll be looking at here with this normal curve. And like I said, these percentages are all the same. We'll flip it on over to the next page. I'll let you try example 3, give you a chance to run through one of those again. We'll move on down to percentiles. This is a formula that's on your formula sheet. Commonplace that you've probably seen percentiles, it would be, if you've ever taken a standardized test score, or your child, or even when newborns are, whenever they go for their checkups, they're always given a percentile ranking based on their height, their length, their weight, and that sort of thing. So I'm going to look at here, a class ranking, but just know that it can apply to other things as well. Formula, it's on your formula sheet. It says the number of scores lower or equal to the particular data score that you're looking at, divided by the total number of scores in that population. You're finding the percentile, so you'll multiply it times 100. Just to sort of give you an example, say for example you were at the 80th percentile in your class, then that means that 80% of the scores are at yours or less, and 20% of the scores were above you. So if you're at the 80th percentile, then 80% of the class is doing at your level or worse. There's only 20% of the class doing better than you. So the higher your percentile ranking, the better, the better off that you are. The example that we're going to look at here, I've already put the data in order. It's important because since your formula tells you have to be the number of scores lower or equal to your data score, it's easiest if your data is already in order. These students were taking in a math class, they both got an 80 on the last test, and we want to figure out, well, what's their percentile ranking in their class? So here's Jill. We want to figure out the number of people in her class that got an 80 or less. So here, since she got an 80, we don't know which one of these 80s is hers, but it doesn't matter, because according to your formula, it says the number of people that got that score or lower. So, even though she tied with somebody else, they all need to be included. So I'm going to add everybody from here back, and you would find that would be 13 students that got her score or lower, divided by the total number of students in the class, which would be 17, times it by 100. That would put her at the 76th percentile. Important. What does this mean? Jill then performed better than 76% of her class, while 100 minus 76, 24% did better than her. Okay. Likewise, let's do Bill's percentile ranking. This is Bill's class. He's just below there. For Bill, he also got an 80, but there were more people that got his score in his class, so we would be looking from here over, adding up all of those, and you would find that there were also 13 that got his score or lower, but he had a few more people in his class. He had 20 people in his class, so 13 divided by 20 times 100. That would put him at the 65th percentile. So that means that Bill performed better than 65% of his class. And if we want to figure out what percent did better than him, I just always do 100 minus 65. 35% did better than him. Okay. And the next example, just as a way to make sure that you understand what the idea of a percentile means. Suppose you take your child for their 6-month checkup. His weight's 16 pounds, 9.5 ounces. That puts him in the 58th percentile. We want to know what percent of the children at that same age weigh more than your child. This particular weight class at this particular percentile, that means that 58% are at that weight or lower. That weight or lower. So since in this particular example I want to know how many weighed more than that, then I'm going to do 100 minus 58, which gives me 42. And that would be the answer to my question. 42% weighed more. Okay. If you flip it on over then to your last page, it just talks about where would you maybe perhaps be asked to utilize a bell-shaped curve and also some misuses. This top example just is something that we found online, which was very telling of where a school had asked its instructors, teachers, to sit down with parents during parent-teacher conferences and show where their particular student lied on this scale. And it was basically designed to help them figure out, an individual education plan for that particular student. Are they here in the average? Are they above average? Are they below average? Just, essentially, it was used as a graphic to help explain to the parents where their student lied, and I guess also then explain the motivation for the plan that they had put in place for their child. And then lastly, there are, with everything that's used correctly, there's still oftentimes things where they're used incorrectly, and bell-shaped curve is not immune to that. Things that aren't measurable here, for example, strengths and weaknesses, just trying to put weaknesses on the right and strengths on the left, and most people are okay with things right in the middle, and this is not a good representation of using a bell-shaped curve. Likewise, trying to show that your political affiliation falling in on a particular bell-shaped pattern is also not a good representation either. It is best used for quantitative data, numerical data, not just this, like I said, basically these word forms here. So that will conclude this section.